Hello, everyone. Today I'm presenting the paper Igor, Crash Deduplication through Root Cause Clustering. And this was published at CCS 2021. I want to start this presentation with a simple story. Imagine you run a fuzzer overnight, and in the morning you wake up and it says, I found 10,000 crashing inputs. At first, this sounds like a huge success until you realize you might be looking at the same bug repeated thousands and thousands of times. Plus, on the flip side, a bunch of crashes that look similar but actually have different underlying bugs. So the core question today is how do we turn a mountain of fuzzing crashes into a small, accurate list of unique bugs? That's what Igor is all about. Quick question for you to think about. If a fuzzer finds 10,000 crashes, how many unique bugs do you guess that usually represents? 10,000, less than 10,000, more than 10,000? Just keep a number in your head and we'll come back to this. Where Igor really fits in the fuzzing workflow and pipeline. Before we get into the contents of the paper, I want to place it in the overall bigger fuzzing pipeline. In a typical workflow, a fuzzer generates inputs. The target program crashes, and we end up with a large set of crashing test cases, or otherwise known as POCs or proof of concepts. So just like our project that we worked on in phase one, we are generating inputs like it was just our binary, our three-digit binary, and then the target program crashes. And then we end up with the crashing test cases. But there is a bigger challenge than just collecting the crashes. It's actually making sense of those crashes. And this takes developers a lot of substantial effort and time to analyze each of these crashes and each of these crashing test cases. And inaccurate crashes or crash grouping and identification can waste a lot of precious developer time. So Igor doesn't try to just find the crashes faster. Instead, it actually targets the exact step in the pipeline where we actually group the crashes together to identify them so that we can actually better connect many of the crashing inputs to the actual unique underlying bug. And the question to keep in mind as we go along in this presentation is when fuzzing produces a huge number of crashes, what matters more for fixing bugs? Does the number of crashes matter, or actually how well we can group them into bugs and in categories that actually need to be fixed? I want you to keep that in mind as we keep going. So I've mentioned crash duplication. So let's actually define what crash duplication even is. A fuzzer produces many crashing inputs, sometimes, as we were talking about, called proof of concepts or POC. Each POC can trigger a crash, which it should, but not every crash technically corresponds to one unique bug. It's not a one-to-one ratio at all. So crash deduplication tries to answer which crashes are likely caused by the same underlying root bug, because multiple crashes can be actually tied back to one bug. And if we do duplicate perfectly in a perfect scenario, each bucket or each group equals one unique bug. That is the ideal situation. And on the flip side, if we duplicate badly, we waste time, either by investigating duplicates or we accidentally merge different bugs into the same crash bucket group. So, in short, crash duplication is basically mapping from thousands of crash inputs and bringing it down to a manageable set of actual bugs and bug candidates. Common deduplication techniques. So, what in the real world, what do people commonly use and do to actually get crash duplication? One of the most common approaches is stack hashing. And this is where we're taking the call stack at the time of the crash and we hash it. So we get an ID for it. And we use that ID to hash and put in a hash table and identify crashes in order to put them in groups later on. Another approach is directly looking at the crash site. And this is meaning that we can just literally look straight at the memory address of where this crash is occurring. And that's just the way we're going to identify it is just to use that address. It's honestly a really cheap and easy way to do it. And another common approach that's mentioned in the paper is a coverage profile. And a coverage profile is basically which edges or basic coding blocks were executed. And we're going to use those edges and that code as the bug identifier, as the ID. These techniques are popular because they're very fast and simple, and they often work reasonably well. But the paper says that these bug identifiers, like coverage profile, stack hashes, and crash sites, can actually, in so many cases, misclassify the bugs because fuzzing at times can amplify small differences and fluctuations and actually produce more noisy code that's unrelated to the root cause. And we will get more into that as we get into this presentation. Two failure modes. There are two classic ways that deduplication can really go wrong. First, it can inflate the actual bug count. This means that one singular underlying bug can actually be split into different crash buckets. This can happen for many ways. One example is that like when the stack trace or the coverage profile is just varying because like we were talking about, fuzzing can amplify small fluctuations and changes and just like a different path. And when even though the crash and the crashes were from one underlying bug, it can be split into multiple buckets because of these small fluctuations. Secondly, on the flip side, we can falsely group and conflate the unrelated bugs, meaning different bugs, instead of being in different buckets, they're getting into the same bucket as a group. And this can happen where crashes share that similar crash site address. Like if two crashes happen to happen at very similar memory addresses, then they're going to get grouped into the same bucket. And even though they're completely unrelated bugs. So this is kind of a quick question to the audience so far. Is which failure kind of feels worse? Like what would you rather have? What would you rather not have? Would you rather have the inflating bug counts where we have just one bug that's split among multiple crash buckets? Or the other way where we have unrelated bugs in the same bucket? Igor's goal is to reduce both of these problems by grouping the crashes in a way that better reflects the underlying root cause. Why fuzzing output is noisy. I want to kind of make this topic a bit more concrete and like a bit more clear just by talking about an example. And the example is that let's just imagine we're fuzzing an image parser. So let's just suppose this fuzzing program has multiple stages. It first detects the file type. Then it's going to parse the header, allocate the memory addresses, and then it starts decoding the actual pixels. So let's suppose that in this, there is one real bug. Let's suppose that there's a bug that only triggers when there's a particular field in the header and it has a specific pattern, kind of like in phase one of our project with our specific 3 byte combination. So here, a fuzzer running it on this image might generate hundreds of crashing test cases. Even though they trigger the same underlying bug, small input differences can send execution through different error handling paths or different branches. So this means that the observed stack hashes can fluctuate and change, even though it's the same underlying bug, just because of those smaller input differences. In this situation, a deduplication technique based on stack hashing, this is where it could split the bug into many buckets, even though the IDs or even though the crashes are from the same underlying bug, these small input differences could cause that and cause the to inflate the bug count. Now let's imagine there's a second unrelated bug. somewhere else here and here, if the crashes end up looking similar at the crash site, a bug identifier could just group them together. Even though they're completely unrelated, they might be grouped in the same bucket. So the main point of this example is just to show like that fuzzing can introduce so many fluctuations and produce so much noisy code that's just unrelated to the root cause. And it just, at the end of the day, it's just going to confuse the crash grouping, and it just doesn't even make any sense to group the crashes at that point. So I made a key observation, I guess, from reading the paper. And this is a key observation that like I feel like Igor builds on, is that crashing fuzz inputs, so any input that actually causes the crashes, can actually execute a lot of irrelevant code before crashing. In other words, the way you can just say this is like the execution path contains noise. And this noise is just a bunch of code that is unrelated to the actual crash. Like you could have a ton of code, and there's actually only a couple lines there that are causing the crash with the input. So if we actually compare just two crashes using a full stack or a full stack trace, we're comparing a bunch of extra stuff and extra code that is not really related to the root cause, even though there's some little code in there that is. So Igor's idea is to reduce that noise first, get rid of that extra stuff. So whenever we start using the bug identifier, it's more likely to really reflect the true like behavior that was actually triggering the bug and not with all this extra noise. So this is where we're going to get into Igor's specifically. And this is an overview. And we kind of split it into two phases here. And I'm going to call them phase A and phase B, just for simplicity's sake. So Igor is a two-phase pipeline. Let's just say phase A. Phase A works like this. For each input that causes a crash, we are going to produce a new input that also causes a crash, whose execution trace is as simple as possible, meaning it's executing fewer edges and less irrelevant code. So each input might have a bunch of code attached to it. We realize, okay, it crashes. Now we're gonna get rid of all that extra noise and then just produce that new input while still making sure it crashes. Phase B of the pipeline is now we're going to convert that new simplified execution into a structural representation. And this structural representation will end up being a graph. And once we have the graphs and the data, we can cluster those crashes based on similarity, with the goal that each cluster corresponds to one unique bug. So the theme is we're going to simplify first and then cluster second. That is the central way that Igor is going to work. Input versus execution. This slide is pretty important because you may believe that minimizing input means that the execution is to be simplified, but that is just not the case. Many fuzzing workflows already do input minimization, meaning they are making the input smaller and smaller while still preserving the crash. That's obviously great for debugging because now you're figuring out, okay, this input is crashing it, but can we reduce this input and does it still crash? And if that is still the case, that's great, right? Because now we're not having to create such a big input for it and it still crashes. But however, input size, just because we're making it smaller, doesn't mean the execution complexity is going to be smaller. A small input can still trigger a very complex pipeline. It can still go through format detection, check the header multiple times, and a lot of code logic before really hitting the bug. And that is completely unrelated to the size of the input. That's just how it might work. So even though the input gets shorter, the program is still walking through tons and tons of code, and that doesn't really help us because the execution is still so complicated. So this is where Igor is going to focus more on trace minimization. The goal is keep the crash, but reduce the execution. Have fewer edges, fewer branches, and less noise and unrelated work completely. If you could think of the crash as kind of a group or kind of a combination of a root cause plus noise, Phase A is trying to remove as much noise as possible. Igor fuzz. So, we talked about minimizing the trace, but we didn't really talk about how that actually works. So, how do they really minimize the trace? They introduced something in the paper called Igor fuzz. Conceptually, it's just a fuzzer that keeps mutating the crashing input, but it uses a different function than a normal coverage guided fuzzer. Because a coverage guided fuzzer usually would reward more coverage. If there's more coverage happening, we're going to keep going down that path and using that input. But in Igor's case, actually, it's rewarding less coverage as long, and this is the big one, as long as the program is still crashing. Because if it gets less coverage and it's not crashing, then it's no good anymore. But as long as it's still crashing, it goes along the line of less coverage. So it's searching essentially for an input that executes the fewest edges and the fewest hit counts as it can. And the paper calls it like minimum coverage fuzzing. This is pretty smart because it's using the fuzzing itself to simplify the execution trace and not just reduce input bytes. So the output of this is like you want to get a crashing input that reaches the crash through the most direct and less noisy route as possible, making it scalable. At this point, you may ask, I did ask this too. If we're doing this for every crash, like every crash you do, you are getting rid of the noise and creating new input and doing this over and over and over again, this is going to take a long time, right? So obviously, the creators of Igor thought about this, and they're including like practical scaling choices in this. Like, first of all, if there's any like crashes that look obviously related, like I mean, they're just gonna look related, like sharing the same stack or the stack hash ID or some similar ones. Igor's not gonna really fully do the entire process on every single one. Like, if there was a group that are obviously a group, it's going to just sample one of them just to see what bug it is and just assume that the ones that are next to each other are going to be similar. And this is still allowing it to see the different causes and the different bugs, but it's not wasting as much time. Like you have to have that sacrifice there. And secondly, it uses like beforehand, it'll minimize the input. Like even though minimal input and shortening input itself doesn't always just do the full job, it still is helpful. So it's Igor fuzz is going to reduce the workload, or I'm sorry, Igor would reduce the workload and use an existing input minimizer. Just so that later, when we're doing the heavier trace simplification, there's not as much to simplify later on. So the creators of Igor are very aware that the deduplication has to handle huge crash volumes, and this is very apparent here. It's representing the simplified crash as a CFG. CFG stands for control flow graph, by the way. So now we're moving to phase B. After phase A, we have simplified the crashes. Igor is now going to build a representation from each of those simplified executions. More specifically, these representations are control flow graphs. And this is going to be based on what's executed in the minimized trace. But why do this? Why even create a graph in the first place? Because graphs, they contain structures, specifically in this case, branches, loops, and most importantly, the shape of the execution around the crash. So instead of comparing two crashes by, let's just say, did they both hit this edge or both be in this group, like they're now comparing, like Igor's going to be comparing it by the shape of the graph. Do the actual graphs look similar? And the hope is after removing noise, if the graphs do look similar and the shape of the graph is going to be closer to the real root cause because there's not as much noise ruining the shape. Similarity in clustering. So we might be asking, how do you really even compare two graphs? Like, how is Igor doing this? Well, Igor's using a certain technique of graph similarity, and it's called Wiesenfelder-Lehmann subtree kernel. I'm not going to get into all the nitty-gritty math stuff of this because I believe like the conceptual part is kind of enough to explain this. Conceptually, it's creating a similarity score based on whether two graphs have similar local structures. Like, for example, like if around the nodes, the structures just looking similar or have the same distance between the nodes, it can use that distance metric and say, okay, now since we have the same distance here, it's going to create that score. After computing these distances, these similarities, Igor is now going to cluster the crashes. The paper specifically mentions spectral clustering, which is a very common way to cluster when you have these types of similarities. So in plain English, this phase is turning each simplified crash into a graph. And since it's simplified, now we can compute how similar the graphs are by finding the distances using the metric. And then once you have those distances, you can group them into clusters that ideally will match the unique bugs. Quick audience question. If two crashes are from the same bug, what would you expect their simplified graphs to share? An answer I'm thinking about is they would probably have a similar shape, especially around the path and the part that triggers the bug. Now I want to kind of connect this back to the human part and the human workflow, because at the end of the day, that's the entire point, right? Like let's just imagine that you and I, we're engineers and we're on a call and we're working on a project. You open up your dashboard and you see that you got 5,000 crashes from your fuzzer. We're initially very happy because that's great. However, if our crash grouping is just crude, like we might get hundreds or even thousands of groups and buckets, and now we're gonna spend hours opening duplicates. We're gonna get really tired of this, and at the end of the day, we might not even find the most important bugs that we need to because they could be buried under so much other duplicates. And if the crash grouping, however, was more accurate, like using Igor, we could spend less time sorting through repeated crashes and more time actually addressing the bugs and fixing them. So, Igor is essentially trying to trade in a bit more computation energy versus us as humans kind of putting in a lot more energy there. And I'll ask this a question. Is fuzzing limited by CPU time or human time? In many real settings, it is human time. And this is why this paper and Igor matters so much. I'll finish this presentation with the results, limitations, and big takeaways. The paper evaluates Igor on fuzzing datasets, and these were covering 254,000 crash POCs across 10 programs, corresponding to 39 uniquely identifiable bugs. The headline result from all of this is that Igor groups these POCs into 48 uniquely identifiable clusters, 48 different clusters. Like that's crazy because the other competing techniques are producing clusters that are just much larger and less uniquely identifiable. So the claimed impact from the paper is that Igor is helping avoid the two main deduplication failure modes that the paper was highlighting. Like it's not inflating bug counts and not falsely conflating unrelated bugs. This all seems amazing, but of course there's limitations because every single approach is going to have its trade-offs. First, there's engineering and computation overhead. Like Igor's approach involves a lot minimizing coverage, building the graphs based on representations and data, and clustering. And all of this is just a lot more heavier on overhead than just a simple stack hashing fuzzer. And secondly, this approach really does depend on the quality and more specifically the stability of the executions. Like if the executions are varying a lot, the simplified traces and then the graphs that are made from those traces are just going to be a lot less consistent and a lot less comparable. And the shapes won't really help us at that point. Third, there's just other limits, like two different bugs in the same code region. might just produce the same kind of shape on a graph. We can't really do anything about that. Like there's just a chance that's gonna happen. And those bugs just might just be difficult to separate, even though they're completely different, they might still get grouped together. So I have a couple takeaways from this paper. The first one is crash deduplication is very hard. It's super hard because fuzzing executions just have so much going along with it, like noise, and it's just a lot of work to get rid of that noise. My second takeaway is that Igor's key idea um, is to minimize the coverage and use that fuzzing to reduce specifically the noise and get a simplified execution, the crash triggering execution, instead of just reducing the input bytes. My third takeaway is after simplification, you can just cluster crashes using graphs. And it's such a smart way to group these together and classify these. I just thought that was very interesting. And I'll end with a question for the audience to think about. If you were designing a fuzzing pipeline, would you rather spend extra computation energy to get a cleaner duplication? Or would you rather just keep it simple, use a simple stack hashing fuzzer, and just accept the noisy and the duplication and all of those buckets at the end? Thank you. And before I end, you should read the paper yourself. And I put the published paper link on the screen right now. Thank you for listening.